All right, one more video for you for acid bases. Hopefully you guys are finding these helpful. This is the second problem of that packet you guys did on Tuesday. I had 3 problems on Tuesday when I was out. We just did the first one. This is the second one with 2012 again, number 1. We have a 1.22 gram sample of pure monoprotic acid, HA, dissolved in distilled water. The HA solution was then titrated with 0.25 molar sodium hydroxide. The pH was measured throughout the titration, and the equivalence point was reached when 40 milliliters of sodium hydroxide solution had been added. The data from the titration was recorded in the table below. So let's just check out this data first before we go on and actually look at anything else. Okay, that's what you guys are notoriously not good at, is actually looking at everything before you actually examine the problem. So before any sodium hydroxide is added, we're not given a pH. That means we're probably going to be calculating it a little bit later. Once 10 milliliters are added, we start increasing our pH. Okay, 20 milliliters, 30 milliliters, 40 milliliters. Okay, this is our equivalence point. I'm going to put a mark by it to keep track of it. And then 50 milliliters is past that, which means now we have more sodium hydroxide, so we're starting to get into that much higher basic solution. So just kind of thinking through what a titration is. We have the acid that we're starting with and our little flask. Okay, that's a really bad flask. There we go. We have our acid, HA. We're dropping in our base, NaOH. And we're watching for a pretty little color to change in here, and we're getting the pH once that color changes. In this case, we're not really looking at the indicators so much as just looking at the concept. Okay? All right, so now that we've kind of got the basic gist of what's going on, let's see what the question's asking. Explain how the data in the table above provides evidence that HA is a weak acid rather than a strong acid. So what information do we have to do this? Not much if we try to go based off of our initial pH, which can we use pH to determine if something's strong or not? No, it's got to have both factors. So pH is based off of the hydronium ion concentration. The stronger the acid, the more the concentration of hydronium ion that will be present per the same amount of moles of a weak acid. So it's all about looking at the amount of moles of the acid and how much of those moles actually dissociate. So I can compare two acids, such as, let's say, HA, a strong acid, and HA, a weak acid, HCl, a strong acid. If I'm looking at 1 molar solutions of both of them, I can compare their two pHs, and I can tell you the pH of HCl is going to be lower because if it's strong, it's going to have a much higher concentration of hydrogen ions than HA, which is weak. So I can do this type of analysis, but I can't just look at a pH and be like, oh yeah, it's weak because it's this. That doesn't happen, nor can I do the same thing for strong. The only way I can make that determination is by comparing molarities and all that fun stuff. But what I can do is look at this guy right here, my equivalence point. The equivalence point of a strong acid, strong base titration, which NaOH is a strong base, would give us a pH of 7 at the equivalence point. Well, why? Well, because the conjugates, let's just say we're doing HCl and sodium, sodium hydroxide, we would end up with the conjugates of sodium ions and chlorine ions once the reaction occurs, and neither one of these are going to react with water, therefore no reaction occurs. So think about it this way, sodium hydroxide plus hydrochloric acid forming sodium chloride and water. Well, water doesn't affect the pH of water, so we're not going to worry about it. Then we look at sodium chloride and we recognize that sodium's not going to form sodium hydroxide, so it's not going to affect the pH of water. Chlorine's not going to form HCl, so it's not going to affect water, so our pH is 7. However, if we have a situation where we have NaOH with a weak acid, HA, reacting to form NaA, and water, again, we don't care about the water, Na is not going to change the pH just like we talked about, but A might. If A is a conjugate base of a weak acid, it is able to steal a hydrogen from water, forming HA and OH ions. And this production of OH ions makes the salt, the anion of the weak acid, basic. It's a conjugate base, so it makes our pH basic, so 8.62. So because our equivalence point is 8.62, which is basic, it tells us that we have a conjugate base, left over from the reaction, or formed from the reaction, which then reacts with water to produce hydroxide. And the only way this reaction will occur is if A is a conjugate base of a weak acid so that the weak acid can form in the first place. So kind of a long-winded explanation, but that's the gist of it. All right, then write the balanced net ionic equation between sodium hydroxide and HA. So HA we're going to keep together because it is a weak acid and does not dissociate completely. NaOH we're going to dissociate and just have OH. It's going to form water and our A ions. Pretty straightforward. Calculate the number of moles of HA that were then titrated. Well, how are we going to do this? Again, MaVa equals MB VB would still be my fallback. Okay, so if I go back up here, I'm told we have, oops, sorry, this is being a little spastic. We have a 0.25 molar sodium hydroxide solution, and we used 40 milliliters of it. Okay, so let's jump. And actually, we don't have enough information to do MaVa equals MbVb because all we have is grams. So we're just going to have to use the definition of equivalence point, which is the moles of the acid equal the moles of the base. And we have enough information to determine the moles of the base because we're told we have 0.040 liters, or 40 milliliters, times our molarity of 0.250 moles per liter, and that is going to give us 0.010 moles of sodium hydroxide, which is equal to 0.010 moles of the HA. Okay, so from there, it then tells us to calculate the molar mass of HA. Well, what in the world is that? We haven't seen molar mass in forever in terms of calculating it. Okay, no big deal. It can be thrown in anywhere. Molar mass equals grams per mole. Well, let's go back up. We know the grams was 1.22 of the acid. We also know that the amount of acids that reacted was 0.010. So 1.22 grams over 0.010 moles. Okay, and we get that number, which is 122 grams per mole of our acid. No big deal. All right, let's keep going. The equation for the dissociation reaction of HA and water is shown below. Assume the initial concentration of the HA solution, before any sodium hydroxide is added, is 0.2 molar. Determine the pH of the initial HA solution. So again, going back up here, we don't have the initial pH. Guess what they're making us do? They're making us calculate it. So how do we do that? Ice table, as always. Okay, so we set it up. And we're told we have a 0.20 molar solution. We don't care about water. 0, 0, minus x, plus x, plus x. 0.200 minus x, x, and x. And then our Ka is equal to hydronium times the anion over HA. Okay, which is going to result in 6.3 times 10 to the negative 5 equals x times x over 0.200, because again, 0.20 minus x is essentially 0.20 because k is small. So 6.3 times 10 to the negative 5 times 0.2, take the square root of that, and we get an x value to be 3.55 times 10 to the negative third molar. Now take the negative log of that for our pH, and we get a pH equaling 2.45. So nothing we can't do, right? All right, last but not least, last one, F. Calculate the hydronium ion concentration in the solution after 30 mils of sodium hydroxide is added and the total volume of the solution is 80 milliliters. All right, so let's go through and think about this. We have our reaction, which we want to go back up here and grab this reaction, HA plus OH, forming H2O and A minus, because we need to have the reaction between the acid and the sodium hydroxide to figure out how much acid and anions are present at this point in time. So we start with 30 milliliters. I'm actually going to move this down a little bit. Give me a second. Whoops, grabbed the wrong thing. Let's try that again. There we go. so I have some room to write over it. We have 30 milliliters of this guy, and we're told it is 0.25 molar. We're also told that we have 0.200 molar, and we have a volume of 50 milliliters. We get that from the fact that we've added 30, there's a total of 80. The difference is what we had originally of the acid, which is 50. So we want to do moles here because of stoichiometry. So 50 times 0.2 is going to give us 10 millimoles, or if you guys would rather, we could do 0.05 times 0.2, which will give us 0.01 moles. Whichever one works better for you is your call. I'm going to work in moles for this point. Okay, so 0.075, 0, don't care. We have our limiting reaction. Oh, I'm sorry, that's 0.0075, my bad. Limiting reactants, this guy, so 0.0075. We set that up. We're left with 0.0025, 0, and 0.0075. From here, we have to recognize that equilibrium is going to be reestablished between these two species, and we need to recognize that we do have a buffer. So if we were asked for pH, we could very easily plug this into the Henderson-Hasselbalch, but we're not asked for pH, we're asked for the hydronium ion concentration, which does mean we're going to need to do our ice table again, unfortunately. It means a little bit more work, though technically, I guess you could technically solve for the pH using the Henderson-Hasselbalch equation and then just convert that to the hydronium ion concentration. I suppose it could work either way. That's kind of an up to you thing. Now I'm going to divide these numbers by 0.080 to get my mole values. Give me just a second. All right, and we get for this guy 0.0313. And for this guy, 0.0938. 0, don't care. And we're going to run through our ice table again real quick, or at least that's the way I'm going to run it. There are other ways to run this. It's kind of up to you. What I do want you to recognize is that our pH is going to be higher than it was initially before any sodium hydroxide was added, because we now have some anion here, which is pushing the equilibrium back towards reactants a little bit, resulting in less product formation, therefore less hydronium. Okay, what is our Ka value? 6.3 times 10 to the negative 5 is going to be equal to 0.0938 times x divided by 0.0313. So we do that math, 6.3 times 10 to the negative 5th times 0.0313 divided by 0.0938, and we get an x value of 2.10 times 10 to the negative 5th. Okay, and again, that's our hydronium ion concentration, so we are done. And if we were trying to find our pH, we could just take the negative log of that, which is going to give us around 4, and if you want to double check to make sure that makes sense, jump back up here, and it probably would, because that looks exactly like where we are with that 4.2. More specifically, this one would give us 4.7, which again makes sense that if this was 4.70 or 4.68 in all reality, it does make sense that it is higher because we've added more base, so we now have more anion of the acid in there, therefore shifting the equilibrium back over towards the HA, resulting in less hydronium, like we just talked about. So it is going to be a little bit higher pH, but also notice it's not a huge change in pH, and that's because after the point in time when we start adding sodium hydroxide, we end up in that buffer region where we have some acid and some anion, so our pH is not changing super dramatically. Whoops. Which we can see down here in our math. Sorry, I'm not sure what it just did, but it just grabbed stuff and moved it. But down here we can see some of the acid, some of the base present, and that's going to be true at any point in time once we add sodium hydroxide. All right, guys, that's it. Thanks.